In this video lecture, we will discuss the elimination of drugs and toxicants from the body. The learning objectives for this video are to describe the processes of renal filtration, reabsorption, and secretion, and how they impact elimination of a drug or toxicant, to predict how the physicochemical properties of a compound will influence renal elimination, to understand how compounds can be eliminated through bile, and explain why metabolism can facilitate renal and biliary elimination. Elimination is the removal of a drug or toxicant from the body as the parent compound or as metabolites. Recall the example of acetaminophen metabolism. And now we will go through the types of elimination they will undergo. The kidney is the main excretory organ, which eliminates many compounds through urine. The liver also plays many roles in elimination by excreting compounds through the bile. Other organs play a minor role in the elimination of drugs and toxicants. Some are eliminated through exhaled air, sweat, saliva, and breast milk. To understand elimination via the kidney, we must understand the fractional units that make up the kidney, the nephron. The nephron is the functional unit of the kidney. There are a number of regions of the nephron, all with different functional roles. The glomerulus consists of a network of capillaries where blood is filtered into the renal tubule. In the proximal tubule, a large extent of reabsorbed of ions, water, glucose, amino acids, and other essential compounds occur. The loop of Henle is responsible for creating the ion gradient in the medulla that helps concentrate the urine. In the distal tubule, a large portion of water and ion reabsorption occurs. This is also the primary site of hormone-based regulation of ion and water balance. We will not discuss the functional regions of the kidney in great detail during this video, but it may be helpful to review some renal physiology to better understand how it is applied to renal elimination of drugs and toxicants. Let us go over a simplified version to get a better idea of what processes are important for renal elimination. A compound will enter the system through the afferent arteriole, which splits into glomerular capillaries with large pores enveloped inside of the Bowman's capsule. Most compounds in the blood will be filtered freely through the capillaries and into the tubular fluid, unless they are bound to plasma proteins, which are too large to be filtered. Anything that is not filtered will leave through the efferent arteriole, which follows the renal tubule and later branches into the peritubular capillaries. From the peritubular capillaries, a compound can be secreted into the tubule. Compounds inside the tubule fluid can also be reabsorbed into the bloodstream. At the end of the nephron, whatever is remaining in the tubule will be excreted in urine. So the amount of compound excreted is equal to the amount filtered minus the amount reabsorbed plus the amount secreted. These principles apply to any compound found in the blood. However, the excretion of compounds differs because of size, physicochemical properties, and the presence of transporters within the renal epithelial cells. The formation of ultrafiltrate within the tubule is driven by the pressure difference between the afferent arteriole and the initial portion of the renal tubule. The main factor that determines whether a compound will be filtered is its size. Think of the glomerulus like a coffee filter or a strainer you might find in your kitchen. Size is the limiting and driving factor behind the filtration. See the drug in blue entering the glomerulus. If the drug is small, all is filtered into the primary urine, but the plasma proteins are too large to be filtered. Now that all the drug has been filtered into the renal tubule, it can be reabsorbed or secreted. Both of these processes will be discussed in detail shortly. The glomerulus is 25 times more permeable than most capillary beds, meaning that larger chemicals can cross. However, there still is a size limitation. Anything with a molecular weight less than 5,000 will be freely filtered, and anything with a molecular weight above 70,000 will not be filtered. Compounds between 5,000 and 70,000 will have some percent filtered. Most of the drugs and toxicants are freely filtered as long as they are not bound to plasma albumin. Albumin has a molecular weight above 70,000, and it is therefore not filtered, so any compound bound to it will also be prevented from crossing the glomerular membrane. This table shows how increasing size limits the percentage of a drug that is filtered. The glomerular filtrate, or primary urine, is typically the same composition as the blood with the exception that there is nothing above 70,000 molecular weight, which excludes red blood cells and most proteins. If these compounds are present in the urine, they are used as markers and indicate damage to the kidneys. As compounds travel through the renal tubules, they can be reabsorbed into the bloodstream. For essential compounds such as sodium and glucose, this is an active process, but for most drugs and toxicants, reabsorption occurs through passive diffusion and is limited to lipid-soluble compounds which are capable of crossing the membrane. Charged and polar compounds will not be passively reabsorbed. You will remember in the metabolism videos that we talked about how metabolism can make compounds more easily excreted by making them more polar. If metabolism makes a drug more polar, it will not be reabsorbed from the tubular fluid, and a greater amount will be eliminated. Also, the pH of the nephron and the pKa of a specific compound can alter reabsorption because they influence the compound's ionization state. The principle that causes charged compounds to become stuck in the renal tubule is known as ion trapping. But first, let us look at what happens to an uncharged or lipophilic compound. When an uncharged and lipophilic compound is filtered at the glomerulus, it will be able to diffuse across the membrane of the renal tubule into the extracellular fluid and then back into the systemic circulation. This process is known as tubular reabsorption. This will prolong the time that the compound remains in the systemic circulation and slow down its elimination. When charged compounds are filtered at the glomerulus, they will not be able to be reabsorbed across the membrane of the renal tubule. Thus, they will remain in the renal tubule and will be excreted in the urine. This is known as ion trapping. Keep in mind that weak acids and weak bases may be charged or uncharged depending on the pH. Therefore, changes in pH of the renal tubule may influence the ionization state and the reabsorption of a compound. Now let us look at some examples of what happens to weak acids and bases and neutral compounds in the kidney. We will start with the weak acid benzoic acid, which has a pKa of 3. Do you think benzoic acid is easy or difficult to excrete if pH is 4? What about if the pH is 8? With a pKa of 3, benzoic acid will be predominantly ionized at a pH of 4 and a pH of 8. The ionized compound will not be reabsorbed from the tubular fluid, and any additional molecules that are secreted will also be excreted in the urine. As benzoic acid travels through the nephron, water will be reabsorbed back into the bloodstream along with sodium and other compounds. As this happens, the concentration of benzoic acid will increase because it is not reabsorbed along with the water. Now take a moment to think about how pH of the tubular fluid will affect the excretion of the weak base aniline. With a pKa of 6, at a pH of 4, aniline will be predominantly ionized, so it will be easily excreted. However, at a pH of 8, aniline will be predominantly unionized, so it will be able to be reabsorbed from the tubular fluid into the bloodstream and will not be easily excreted. Now let us think about what happens to a neutral compound, biphenol, in the kidney. It is freely filtered and lipophilic, so it will be reabsorbed easily. The pH of the tubular fluid will not influence the reabsorption. Instead, the driving force behind biphenol reabsorption will be the concentration gradient in the tubular fluid compared to the extracellular fluid and blood. Therefore, as water is reabsorbed through the nephron, biphenol will also be reabsorbed to maintain the equivalent concentrations. The concentration of biphenol will be the same at the early portions of the nephron as it is in the final urine output. But much of the biphenol will be reabsorbed into the bloodstream along with the water. Compounds in the peritubular capillaries can be secreted into the tubular fluid by active transport across the renal epithelial cells. Because this process utilizes transporter proteins, it is saturable, meaning that there is a limit to the amount of compound that can be secreted at a given time. These transporters are also subject to competitive inhibition, so compounds that utilize the same transporters will inhibit each other's secretion. Now let us look at an example of digoxin, a drug taken for heart failure. Digoxin is taken up into the renal epithelial cells by uptake transporters and secreted into the tubular fluid by efflux transporters P-glycoprotein. When given alone, a portion will remain in the blood at a therapeutic concentration. However, if the antiarrhythmic drug quinidine is given at the same time, it will compete with digoxin for the uptake transporter. Competition inhibits digoxin secretion and a large amount will remain in the blood. Digoxin has a narrow therapeutic index, so this increases the amount that remains in the blood and may cause toxicity. There are a number of different transporters that contribute to the renal secretion of drugs and toxicants. You are not expected to know all of these transporters present in the renal epithelial cells, but keep in mind there are a large number of different transporter families and that many of these transporters can be found in other cell types as well. Clearance is an important concept to understand in renal elimination of drugs and toxicants. Clearance is the volume of plasma that is completely cleared of a solute per unit of time. This does not tell you how much drug is actually eliminated, but the volume of plasma that is cleared of the drug. To determine the rate of elimination, which is the actual mass of the drug cleared per unit of time, you may multiply the clearance by the plasma concentration of the drug. Multiplying a flow rate by the concentration, we are left with the value representing the mass per unit time. If a drug is freely filtered and is not reabsorbed or secreted, the clearance will be equal to the glomerular filtration rate because everything that is filtered will be excreted. Now let us discuss biliary elimination. The liver secretes 0.25 to 1 liters of bile a day, and some drugs and their metabolites are excreted via the liver into the bile. In order to be excreted in the bile, a compound must have a molecular weight greater than 300. Most drugs and toxicants are not this large. However, phase 2 metabolism reactions, especially glucuronidation, can make a compound the sufficient molecular weight to be excreted through bile. We are not going to go over hepatic physiology in detail, but we will do a quick review of how compounds get transported from the blood to the liver and into the bile. Blood enters the liver through the portal vein and the hepatic artery, and flows towards the central vein through the hepatic sinusoids. Compounds in the blood are taken up by the hepatocytes that line the sinusoids, where they can be metabolized. From the hepatocytes, some of the compounds and metabolites return to the blood flow. Those that are large enough are transported into the bile canal, where they flow into the bile duct. This figure shows a close-up illustration of 2 hepatocytes and a number of transporters that facilitate the elimination of bile salts and xenobiotic conjugates through the bile. In this figure, the blue and orange arrows indicate typical absorption of lipophilic and hydrophilic conjugated products. This is in contrast to enterohepatic circulation. Enterohepatic circulation is the circulation of a drug or other substances from the liver to the bile, followed by the entry into the intestines, absorption by the enterocytes, and transport back to the liver. Let us look at an example of a drug taken orally that undergoes enterohepatic circulation. First, after orally ingested drug has been absorbed from the gut, it is transported via the portal vein into the liver, where it can be conjugated to glucuronic or sulfuric acid or other organic acids. The conjugated products may pass from the hepatocytes into biliary fluid and from there back into the intestine. Glucuronides can be cleaved by bacterial beta-glucuronase in the colon, enabling the liberated drug molecule to be reabsorbed. In the liver, the drug can then be again conjugated. Glucuronides with the molecular weight greater than 300 enter the bile into the intestines, where the drug may be unconjugated or reabsorbed or eliminated in the feces. Drugs that are subjected to enterohepatic cycling are therefore excreted slowly and show a unique pattern in their plasma versus time graphs. This is an example of what a graph of a plasma concentration versus time might look for a drug that undergoes enterohepatic circulation. The first spike occurs just following oral administration when the drug is first absorbed. Then the plasma concentration decreases as the drug is metabolized and excreted. A portion of the drug eliminated through bile is reabsorbed later in the time course, increasing the plasma concentration. To test your understanding of this material, you should now be able to answer the following questions.